That would be grams of that over 1 mole. Can you do that without a calculator? I think you can. Okay, let's talk about some tips for how to do these calculations. How about we reduce some of these fractions? 90 divided by 2, that's 45. Now, okay, I'm going to do that. That makes it 45. 45 times 0.02. 45 times 0.02, you want me to do it? Well, yeah, you know what? I think we can do that. Check this out. What's 45 times 0.01? It's 0.45. Now double it. 0.9. That's the answer. See what we did now? If you multiply by 0.02, don't multiply that by 0.02, multiply by 0.01 and then double it. It's the same thing. Multiply by 0.01 is really easy. You just move the decimal over 2 places. Yeah.
Would it be 0.19 or 0.9?
0.9. Yeah, 45 times 0.02. Or you could say 45 times 2 over 100. That's 90 over 100, which is 0.9. I like to use fractions. I like fractions way better than decimal numbers if I can't use a calculator. So if you have a number like this and you can express it as a fraction, like that, 2 over 100, well, that makes it pretty easy. So yeah, the answer is 0.9. What do we look for? Grams there of FeOH. You okay with that? How are we doing for time? We got about 10 minutes left. There is a next part that I haven't uncovered. It's not very nice. Yes, sir?
If you had values, would you just have like an excess of the reactants just laying around?
There is an excess of that reactant.
Like if we didn't put 2 NaOH, we only put 1 mole of NaOH and 1 mole of FeCO2.
They don't react in a 1-to-1 ratio though, because every iron needs 2 hydroxides.
So we get half of what we have right now.
Yeah. But that's not an appropriate hypothetical because you have to, I mean, you're not going to make this unless you have 2 of these for every one of those. Okay? So don't not balance it and say, oh, well, because I didn't balance it, I have a different ratio. No, you have to balance it. Okay? This is a typical Zumdahl problem, you know, where they're working you. And now look at part D. By the way, I don't remember what part B was, but I didn't like it enough to have it in class. Calculate the concentration of each ion that remains in the solution. What do you think of that? I'll think so.
Part B.
Just said,
I left it out. There was one, but I just left it. Do you know what to do here? What ions remain? Oh, how about let's do this easier. Is there any ions here that are completely used up and are no longer in solution? I'll give you a hint. There's one. Which one is it? Wes, you know which one it is? Why do you say that? OH is tied up in a precipitate, and since that was the limiting reactant, all of that got used up. This thing all got used up in there. There's where all of our hydroxide has been tied up. Now that hydroxide is bound to the iron on the bottom of the beaker, or wherever the reaction occurred. So we have a 0 molarity of hydroxide. Do we have 0 of iron too? Because that was the precipitate. We don't have 0 of iron. We still have some iron. Remember, iron was the excess reactant? If this is limiting, that means I had more than enough of this. So what ions do we still have that are floating around in our solution? Do we have sodium ions? Yeah, we do. The sodium didn't do anything. It was there as an ion before and never got into a reaction. So we have sodium there at the end. What's the concentration of it? We'll find that out. That's all gone. The iron we had an excess of. Some of it got bound up in a precipitate, but then some of it was excess and is still floating around. Chloride ions, same thing. So yeah, most of this is not so bad. We kind of have to wrap our brain again around, okay, we have to convert to moles, find the limiting reagent, use stoichiometry. But then this is kind of new. This is a little dirty. The truth.
For Fe, you would need to find the amount of grams in the beginning, right? And then just subtract it from the end.
Let's stay in moles, because we're looking for a concentration. Let's not bother with grams. Just keep in moles. And what else did you say? You have to find out how much was there at the beginning?
And then subtract it from how much.
Yes. Yes, you do. Yep. Okay, which one do you want to find first? Which ion?
Fe.
No.
Na.
Na. Let's find Na. Okay, let's do Na. You want to do the hardest one first. Let's not do that. The concentration of Na, and I'm going to remind you, this expression is used all the time where you have the brackets around something. The brackets represent the molarity of. So this is going to say, okay, the molarity of sodium hydroxide is, the definition of it is, it's the moles of sodium. Did I just say the wrong thing? Did I look at that and say hydroxide?
Wait.
Okay, moles of sodium over the liters of solution. Let's see if we can figure out what those numbers are. I think we can. How many moles of sodium are in this solution? We found moles of sodium hydroxide was 0.02. Is that the number of moles of sodium? Would you agree that there were 0.02 moles of sodium to start with? Yeah. And how much got used? None. So there's 0.02 moles at the end. Again, if you have 0.02 moles of this whole compound, that means for every one sodium hydroxide, there's one sodium. Therefore, there's 0.02 moles of sodium at the beginning and 0.02 moles of hydroxide. This is similar to when we were doing the combustion reactions in the last chapter. We had to find moles of carbon and moles of hydrogen and then find the mole ratio. You remember doing those problems? Now for the water, there were 2 hydrogens in every water. So if you needed moles of hydrogen, you had to convert to moles of water, then multiply by 2. You remember doing that? We're going to have to do that over there. You see that thing right there? We find moles of chloride ion, just wait. We're going to have to multiply by 2. But for the sodium, for every one sodium hydroxide, there's one sodium. So the number of moles of sodium is 0.02. I'll go back to my sig figs too. Over the liters of solution. What is the volume of the solution? Was that you, Juliana? What'd you say? 200. Where'd you get 200 from? Our original aliquot, I just love that, aliquot. You got to be a special person to be able to use that word, so don't use it flippantly. Our original aliquot of sodium hydroxide was 100 ml. See that? But then 2 solutions got mixed together. The reason I'm making a big deal of it is it's a common mistake for people to only put the volume of the solution that it originally was in. Whenever you mix solutions together, you've got now the sum of the 2 volumes that you mix together. You follow? And you should be able to visualize this. You had sodium ions in 100 ml. Then you added another solution which did not react with the sodium. So now the sodium doesn't only have 100 ml to swim around in, it's got 200 ml. So it got diluted. Its solution, its concentration is going to go down because it got diluted. So yeah, we had, and we have to use it in liters. That's our concentration of sodium. Yep.
Wait, so you're using the volume of the whole thing, right?
Yes. After the solutions are mixed together, you get 100 of this, 100 of this, pour them together. That's 200.
How about the precipitate? Are you including that volume as well?
Oh, great question. Great question. Now, okay, check this out. A reaction did occur in this solution, right? Do you think that if you have two solutions and you mix them together, will the formation of a precipitate affect the volume even a little bit? I think it would. I think the volumes are going to, the actual volume at the end may be a little bit, would it be more or less than 200? I'm thinking it's going to be less too because you took something out of the solution. However, and the Zumdals are very good about this, you'll see when you do the problems. They'll say, assume the volumes are additive. Just add them up to 200, okay? Now, is it really 200? No. But is it very close to 200? Yeah, it's so close that that little change is negligible. Okay? So, whenever you mix solutions together, you go ahead and assume that the sum of the two volumes is the new volume. It's time to go? Okay. Can I just say one more thing in our last minute together? Without a calculator, what's the answer? If you're not sure when you're dividing numbers, either make fractions out of the top and bottom, that will work fine, or put them into scientific notation. This is 2 times 10 to the negative second. This is 2 times 10 to the negative first. So divide them. 2 divided by 2 is 1. 10 to the negative second divided by 10 to the negative first is 10 to the negative first. You keep the 10 and you subtract the exponents.